Hi everyone, in this video we are going to review the module, The Air We Breathe. And so the way I do my reviews is I split them into two different sections. I have a context section, so that's primarily your facts, the things you just straight up need to memorize. There are rules, there's laws, maybe pollutants you need to memorize, but basically the context section is just basic facts, okay? The second section is my chemistry section, so that's a lot of the application. And a lot of students actually find this to be the more challenging section, and that's usually because you have to take information, memorize it, and then use what's in your brain to apply it to a brand new question that you've never seen before on an exam or a final exam. And so we're going to spend a little bit more time on the chemistry section. At the very, very end, I have 3 different questions that I think are the hardest for this specific material, and that I'm just going to use as a way to give you 3 more examples of what you could be seeing on your exam or on the final exam. So let's start off at the very, very beginning here. We're doing our context section first. So number 1 for context for the module, The Air We Breathe. So the first thing we talked about in this unit was sustainability. Sustainability. And so basically all we're trying to say here is we need a healthy planet. We need a healthy planet. If we destroy this planet, then our children and our children's children literally are not going to be able to survive. And so if we're doing certain things that are hindering their possibility of living and thriving, it's just such a sad thing. So we need to find a way to actually have a planet that we can sustain using our energy sources and everything. So this is the big picture idea. After that, we started focusing primarily on the troposphere. So we know our atmosphere is comprised of 3 different sections, your troposphere, your stratosphere, and your mesosphere. But we're primarily focusing on the troposphere for this section because that's the actual air that we breathe is the troposphere. So now, what you should know is the difference in your concentrations of specific molecules in an inhale versus an exhale. And what you'll see is that your inhale concentrations are going to be very, very similar to what the atmosphere is out here in our daily world. So you inhale 78% nitrogen and you exhale 4% carbon dioxide. And so you just have to know all those numbers and make sure you memorize those. You absolutely need to know that. All right, then we focus on our air pollutants. That was the majority of what we focused on in this unit. And so we had a lot of different air pollutants, but we had 5 specifically that I really harped on. So let's break those down one by one. So the first one I want to focus on is the silent killer, also known as carbon monoxide. So let's get some facts down here. It's the silent killer. It absolutely will cause death. Okay. It comes primarily from tailpipes. That's what we like to say. It's primarily from tailpipes. We also know that we can use a catalytic converter in our car to take those really bad carbon monoxide emissions and convert them to CO2 emissions. So even though CO2 is bad for our planet with global warming, it definitely is much better in terms of something that if we breathe it in, we're going to be okay. We can breathe carbon dioxide. We cannot breathe carbon monoxide. We also know that this is considered to be a primary pollutant. Okay, so it's formed directly from whatever reaction it is that we're talking about. It's not like it forms from another reaction from another pollutant, and then we go from there. Okay, so it's a primary pollutant. Now, we have one specific reaction that we say forms carbon monoxide, and that is called an incomplete combustion reaction. And the chemical equation for this is going to be some source of fuel plus oxygen is going to create carbon monoxide and water. So when we say incomplete combustion, we're saying we're creating carbon monoxide and not carbon dioxide. All right, number 2. The second one we focused on was ozone, which is O3. Let me give myself some more space here. So for ozone, we know that we can detect it by a sharp, clean odor. There's a definite smell when it has when ozone's in your presence. A lot of times you're going to smell this when you're around printers. And we also learned later on that we can create ozone from NO2 and sunlight, so something that's photosensitive. We know that when you inhale ozone, you definitely are going to have some kind of lung damage. It's not good for your respiratory system, so you want to be careful. We also talked about a specific mechanism in which we could form ozone. And so for this one, we said we took NO2. We just said that was photosensitive, so we treat it with sunlight, essentially, and that decomposes to create NO and then monatomic oxygen. From there, monatomic oxygen reacts with diatomic oxygen, and you create ozone, which is great when you're in the stratosphere, but when you're down in the troposphere, we breathe that ozone in and then again have lung damage. Now, when we talked about ozone, we definitely looked at a couple maps. Specifically, we looked at California. And so make sure you review those maps and make sure that if I give you a couple different maps, you could figure out, was this early in the day, was it the end of the day, and you can determine that by ozone concentration. We also know that ozone is a secondary pollutant. So it is not formed directly from reactions that happen here on Earth. Usually we have, just like this example here, we have some kind of reaction, we have another pollutant, it forms something else, and then in the atmosphere, these oxygens here that were formed are able to go and be converted to ozone. So it's really neat, but this is definitely considered a secondary pollutant. All right, so now that was number 2. Number 3, what we have here is SO2. So SO2 is a sharp odor as well, but unlike ozone, we say this is a sharp, dirty odor. Okay, a sharp, dirty odor. This primarily comes from coal power plants. Okay, a lot of times we associate this with soot, so soot on buildings that come from these coal power plants. This is really bad to breathe in because it converts to acid in your lungs, and that is incredibly painful to breathe. It's just like stabbing knives in your lungs. It's terrible. It's not a good idea to do that. Like we said, it forms from coal power plants. So a lot of times what you're going to see is you have coal plus oxygen creating SO2. And we'll touch on that more in Module 4, how that actually breaks down. But for right now, what I want you to understand, coal plus oxygen gives me SO2. And then SO2 is definitely a primary pollutant. Okay. All right, number 4, moving fast. Number 4 is NO2. Now, NO2 has a very distinct brown color. It is terrifying when you see it because you know you've done something incorrectly in the lab. We also know that NO2 is formed from tailpipes, okay? But a lot of it comes from power plants. And we're not going to be specific about what type of power plants here. Again, we'll get into that in Module 4 when we talk about combustion. But for now, we just know we create NO2 from power plants and tailpipes. Now, what happens when you bring and breathe NO2 and get it into your lungs? Well, it turns into acid. So you get acid in your lungs. So just like with SO2, when you have acid in your lungs, it's incredibly painful and it's not a good idea. Where do we get NO2 from? We take fuel, we treat it with oxygen, and you get some kind of NO2 situation. So the same type of combustion reaction happening. We set a fuel on fire using oxygen, and then we get some kind of pollutant. Now, just like with carbon monoxide, we can use a catalytic converter here with NO2. So we have a catalytic converter. Okay. Again, remember, this is what happens in your car where we use a catalyst to convert one molecule to a different molecule. And so for in this example, a way to get rid of NO2 is we use that catalyst to break NO2 apart into N2 and O2. So nitrogen and oxygen, 2 things that just readily exist in our atmosphere. So that's something that's very good. And then the last thing we want to talk about when we talk about NO2 is that it's considered to be a primary pollutant. All right, so now moving on to the last one, which is not my favorite. It's definitely my least favorite, particulate matter, also known as PM. Now, what is it? Basically, it's teeny tiny dust particles, and we talked about how they can be in the solid or the liquid state. Okay, it's not just one or the other. It can be either form. We know that they most often form around fires. So when you have wildfires, you're going to see particulate matter. Well, if you can see it, but it's really, really tiny. We know that this definitely clogs lungs. These pieces or these particles are so small that they get in your lungs and they get in the way so that you cannot easily pass oxygen in and out of your lungs. It's an issue. Now, where does it come from? Just like with before, you take fuel, treat it with oxygen, and you get particulate matter. So when you set things on fire, just automatically you're going to be introducing particulate matter into your atmosphere. Now, we looked at 2 different types of particulate matter. We know that particulate matter 2.5 is smaller than particulate matter 10, okay? And this is just talking about the diameter of the specific particulate matter. Is it a big piece? That would be 10. Or is it a small, something that's 2.5? And then last but not least, this is definitely a primary pollutant. It's created directly from the combustion reaction. All right, still in the context section, moving away from the air pollutants, what we did is we came up with something, I wasn't around, but back in the 1970s, they came up with something to kind of help this or fix this solution so that we don't just kill ourselves and ruin our planet. And so what they did is they came up with something called the Clean Air Act. Now, the Clean Air Act was beautiful because it developed the EPA. And so now EPA is that Environmental Protection Agency that goes around and comes up with a lot of different rules to try to keep us safe and make sure that every human is breathing in good quality air, which brings me to their air quality standards that they created. And if we remember our air quality standards, there were 3 different criteria where we could rank things and basically come up with these standards. How much of one certain pollutant can a human breathe before hurting themselves or actually getting the acid in the lungs? And so that's what these standards are. How much can a person handle? And so they're ranked by 3 different parameters. And so concentration is one of them. The length of duration. So length of exposure may be an easier way to say that. Length of exposure. So how long are you breathing in carbon monoxide? Is it for 4 seconds or 4 hours? Because if it's 4 hours, there's a good chance you're not going to survive. But if it's 4 seconds, you can easily handle that. And then the last one is rate of breathing. So someone who's an athlete and going outside and going like that, they're going to have a high rate of breathing, so they're going to be intaking a lot more of that pollution. Whereas someone who's a couch potato sitting on the ground just being like, barely breathing, they're not taking in any pollution. That's not true. They're taking a small amount of pollution. All right, so after that, instead of talking about just the Clean Air Act, we moved on to the 1990s where we started talking about the Pollution Prevention Act. So instead of just coming up with standards, we're saying, hey, why don't we be proactive about this and try to actually prevent the formation of pollution? And so eventually what they did, or essentially I should say what they did, is they tried to focus on green chemistry. So they tried to make the world a better place. Think about the pollution before you design a power plant or whatever it is you're doing. Actually think about the waste before you go ahead, before you go ahead and try to design whatever it is you're designing. All right, so that's your Pollution Prevention Act. Then after that, we talked about the Tragedy of Commons. And the Tragedy of Commons is basically when you have a group of people or maybe even countries that all use some kind of resource, but nobody is taking responsibility for it. So we saw a couple different maps for this where we had pollutants and then they were traveling from the United States into Canada. And so this is an issue where who's responsible, who's in control. And so it's what we call the Tragedy of Commons. So we need to be very, very familiar with that law and what that concept is in general. The last thing we talked about for our context solution was our indoor pollutants. Okay? And there were 4 main ones that we focused on. The first one we talked about was painting. Anytime you paint indoors, you're definitely exposing yourself to a couple of pollutants. We also talk about candles. Candles often produce either carbon dioxide or carbon monoxide, and so that's something that's definitely bad for you. If you smoke at all, you are definitely exposing yourself to carbon monoxide, so that's terrible. Please, if you decide to smoke, don't do it indoors. You have to go outside. Please, 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 please. And the last thing that we talked about for indoor pollutants was something that we're going to focus more on in 305 in the next semester, but it was basically the decay of uranium and how this happens in your basement, and you can go from uranium to radon, which is horribly bad for you and actually will cause really bad lung cancer. So that's a really bad thing. So these are our 4 main ones that we focus on. Please know there's a significant number more of that, but we just focus on these 3. All right, now number 2. After talking about the context, we started talking about the chemistry. Yay! The favorite part, chemistry. Good. Okay, so now chemistry. First thing we said is we focus on matter. So we know there's 3 different phases of matter that we focused on in this class, solid, liquid, and gas, but we were able to actually take it a step further. So was this a pure compound? Or is it something that's considered a mixture? Now, is your mixture homogeneous by nature or heterogeneous by nature? 1 or 2 phases. It's something you need to be able to distinguish. You also need to be able to tell the difference between an atom and a molecule and a compound. Okay? Please remember that a compound has to have 2 different elements. If you have the same element like N2, that can only be called a molecule. But something like sodium chloride, like this, that could definitely be called a molecule. And in fact, I hate writing that because that implies a covalent bond, so we're going to write it like this. NaCl, compound, okay? 2 different elements have to have that. After we were done talking about matter, we moved on to my favorite table, the periodic table. And we had a lot of different things that we focused on here. So there was a lot of information. So make sure you're super, super comfortable with that periodic table and you know everything that's on there and what it means. So let's talk about the easiest part. We know what the elements are. They're listed on the periodic table. But specifically, make sure you're comfortable with the main chemical symbols. Okay? So you should know that H is hydrogen and N is nitrogen, O is oxygen. The main ones that we've been talking about, you need to just know innately what those are. We also talked about the difference between a metal and a nonmetal. We kind of mentioned metalloids, but they're silly, so I don't focus too much on them. And so we're just focusing on metals and nonmetals. We're going to pretend that says nonmetals instead of non-mutates, whatever that says. And like we said for the periodic table, you should be able to distinguish a gas from a liquid from a solid. And just remember, the colors on the periodic table are going to tell you that. Black is solid, blue is liquid, red is always a gas. That is super important. You need to know that. We also talked about group names. So we have something like the alkali earth metals or the halogens or the noble gases. There are 4 ones that I asked you to know, so you need to make sure you're on top of those. You also should definitely make sure you know that the difference between a period and a group. Okay, remember, group is up and down, period is across the periodic table. Okay, there's 2 different sections. You absolutely need to be comfortable with them. And we obviously know that a family and a group can be interchangeable. We also talked about energy levels. So we know is that as we go down the periodic table, we are increasing in our energy level. We're adding a shell to every single nucleus as we go down the periodic table. And the last thing we did is we started to be able to distinguish or determine what these valence electrons were, actually determine what they are, and know specifically for every single element how many valence electrons are they going to have in the neutral state. After we talked about the periodic table, we moved on to something more fun, which were chemical formulas. We primarily focus on covalent compounds. We kind of ignored ionic because we're going to touch back on that in the 305 or the second semester of this course. So for chemical formulas, the first thing you need to figure out is your nomenclature. There's 2 different sections. You absolutely need to be able to name covalent compounds. We're going to practice one of those in one of the problems that we have at the end of this review. But you also need to know how to name your hydrocarbons. So for this module, I only expect you to know carbon 1 through carbon 4. So I'm talking about methane, ethane, propane, and butane. But all the way in module 4, I'm going to ask you to know carbon 1 through carbon 8. So if you want to memorize those now, absolutely, that's fine. We're going to be using them all semester, so that's absolutely okay. All right, after nomenclature, what we did is we moved into chemical equations versus chemical reactions. So let's get this out here. Chemical equations versus chemical reactions. Now, a chemical equation is what you physically write down. You're trying to give a visual for somebody. A chemical reaction is where you put your goggles on and you're in lab and you're going, I'm making some kind of chemistry thing. You're making a bomb, whatever it is you're making. Reaction, in lab, equation, on paper. You have to know the difference between those. All right, so now, what do you actually have to know about them aside from what the difference is? The first thing is you absolutely need to know how to balance these equations. From here on out, I will expect that you can balance an equation like this, okay? It's something you need to be able to do quickly. By the time we get to Module 4, it's going to be way too much if you're struggling to balance, okay? So you need to get on top of that today. Second thing is you must know a combustion reaction. So this entire semester, we're focusing on combustion reactions. And so there's 2 different versions of them. We have a complete and we have an incomplete. So a complete reaction or complete combustion reaction takes a source of fuel, you treat it with oxygen, you create carbon dioxide and water, okay? It's an exothermic reaction. It's always releasing energy. Now the opposite, not the opposite, a different version of this would be an incomplete combustion reaction. You still take a source of fuel, you still use oxygen, and you still create water. The only difference is right here. Instead of making carbon dioxide that's complete, you were able to put 2 oxygens on the molecule. You only make carbon monoxide, just 1 oxygen, okay? Complete versus incomplete. This is going to come up all semester, so this is another one that you just need to get down. And the last thing we did for the chemistry section of this specific module is we focused on our unit conversions. How exciting! We were able to convert from every single different unit to other things. And we started off by doing pph, ppm, and ppb. You need to be able to go from one to the other. Remember, pph is just another way of saying percent. We also talked about prefixes, and I asked you to memorize all of your common ones. So your kilo, your micro, your milli, whatever it is, the common ones we use, you absolutely need to know those prefixes. There's a chart on Canvas to help you, and you can go through and map all those out. The next thing we did is we talked about scientific notation. Scientific notation. You need to be able to go from a standard number and put it into scientific notation. You also need to be able to take a number that's in scientific notation and convert it back to a standard number. So out of the mantissa and the multiplier, okay? You can't have the time tens to the whatever, okay? After that, we talked about Sig Figs or significant figures. So there's a huge video that explains all the different pieces of the significant figures, and so that's something we'll be focusing on later on in the semester if you need to, but basically for Sig Figs, get it down for this module, and then we're going to kind of leave it for a little bit. They're important, but not super important, so don't get stressed out about them. And then the last thing is we first started to do dimensional analysis here. And we're going to do dimensional analysis all semester. And by the end of this, we're going to be doing such complicated mathematical conversions, I should say, that if you can't get on top of the material today in this unit, you're really going to struggle by the time we get to the very end of the semester. So please, 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 if you stress anything here, it would be this section right here, especially dimensional analysis. You need to be able to do simple conversions. It's just a life skill that I want you to have. All right, that's it for this review. So now what I'm going to do is go through 3 different questions, and I want you to just practice them on your own and then make sure you can do them, okay? So the first one we're going to do here is that Houston has a carbon monoxide level of 23 ppm, and I want you to express this concentration in percent. Go. All right, did you get it? Hopefully you did, but if you didn't, that's okay. Don't worry about it. The first thing you have to do is just rewrite this unit of ppm. So what that's saying is you have 23 pieces of carbon monoxide for every million pieces of air, or components of air, or molecules of air. Okay? But what we're trying to do is convert this to a percent. Well, we know that percent is really pph. So we just want to know what number goes on top per 100. That's all we're trying to do. And if you solve this out properly, you should see that x is equal to 0.0023. So as a percent, your percent is 0.0023%. There's your answer. Next question. What is the coefficient for oxygen in the balanced chemical equation for the complete combustion of heptane? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. Do not worry about it. We'll get it eventually. So let's practice this one together. So the first thing you have to do is come up with your chemical equation. So we're talking about combusting heptane, so C7H16, and then it says the complete combustion. So we automatically know we're adding oxygen. Complete, meaning we're creating carbon dioxide, and then a combustion reaction is always releasing water. So all we have to do now that we've generated our chemical equation, is we actually have to balance it. So the way I personally do this is I start on my left side and I work to the right. So I see that I have 7 carbons in heptane. So I'm going to go right over here to my product side and make this a 7. Now I'm going to come back over here and see that I have 16 hydrogens. So I need to have 16 hydrogens on my product side. So I come over here and I see that I have 2 hydrogens. So the only way to make that 16 is make this an 8. So 8 times 2 gives me 16. So now my carbons check out, my hydrogens check out. The only thing left is I have to balance out my oxygens. So I have 2 oxygens on the reactant side, and I have 7 times 2 oxygens over here, so 14. Plus 8 oxygens on the product side. So 14 plus 8 gives me 22 oxygens. So now I need 22 oxygens on this side in order to make that even. So the only thing I can do right here is go 11 and 2. So 11 times 2 gives me 22. Now I think I have it balanced. Always, always, always go through and check. So I have 7 carbons over here, 7 carbons over here. 16 hydrogens on the reactant side, 16 hydrogens on the product side. Then I have 11 times 2, 22 oxygens on the reactant side, and I have 7 times 2, so 14 plus 8, which gives me 22 oxygens on the product side. So the question is, what is the coefficient for oxygen in the balanced chemical equation for the complete combustion of heptane? The answer is 11. Did you get it? If not, don't worry. Please don't freak out. Go talk to your teacher or email me. I'd be happy to help you with this part. Okay, let's do the next one. Name the compound SiCl4. Go. Did you get it? Hopefully you did. If not, let's do it together really quickly here. The first thing you do is identify what type of problem this is. Is this a covalent compound or a hydrocarbon? Because that's all we know how to name for this class so far. And this is definitely not a hydrocarbon. It's definitely a covalent compound. So for covalent compounds, the first thing you do is you just name your elements, okay? So we have Si is your silicon, and then your Cl is your chlorine, okay? Then you go through and you start to add your pieces in the front here, okay? So your prefixes. So I see that there's 1 silicon right here, so I would write mono. Hopefully red flags are going off when I did that. And then I have 4 over here, so I would write tetra. So now, the one thing you have to do here is remember that you never, ever, ever write mono as the first thing. So think about carbon monoxide. There's one carbon, one oxygen. We only say the mono part for the second piece, the oxide, okay? So you only use mono for the second word. You don't use it for the first. So this is right. Silicon's correct. The tetra's correct. The chlorine, that's pretty close. The last thing you have to remember is that you always change your ending. So instead of INE, you have IDE. So the correct answer would be silicon, tetra, chloride. Did you get it? Hopefully you did. If you did not, drill, drill, drill. Do as many of these as possible until it just becomes innate and you're automatically looking at that and saying, oh, that's definitely silicon tetrachloride. All right, have a great week. Take care of yourself. Drink water.